Okay, so in this example here, which is P13 3 and is taken from the RC Hibbeler book. And again, it is one of the tutorial question from your tutorial sheet. So in this case, we need to determine the initial acceleration of the 10 kilogram smooth collar, which is this collar here. So you need to calculate its initial acceleration, and the mass is given, which is 10 kilogram. The spring has an unstretched length of 1 meter. So the unstretched length of this spring is 1 meter. And in the current position, obviously, it is stretched. So you will need to calculate the acceleration of this collar due to the force of this spring here. So now again, you're also given these distances. So the distance from here to here is 3, and from here to here is 4. And you're also given the spring constant, which is K in this case, and which is 10 Newton per meter. So in this case, what we are given, so you can say that the data in this case, which is given, is K, which is 10 Newton per meter, and mass is given, which is 10 kilogram. Okay, and the spring has an unstretched length of 1 meter. So you can say that the unstretched this is given is 1 meter here, and you need to calculate the requirement here is that we need to calculate the initial acceleration of the collar. So in this case, to solve this problem, first we need to draw the free body diagram here. So in this case, obviously we are interested in the collar here. So we will draw the free body diagram of the collar. So we will draw the collar here, and then we need to identify all the forces which is acting on this collar. So in this collar, obviously one is the spring force, which is in this direction, or we are assuming that the spring force is in this direction here. We can call it Fs, and the weight of this spring is of the collar is in this direction here. This is the weight of the collar, and the normal force is in the upward direction. Okay, the mass is given, which is 10 kg. Okay, now we also need to and obviously this is the need to draw the coordinate system. So we can say that this is our x-axis and this is our y-axis here. Okay, so in this case, now the acceleration we will always assume in the positive x direction. So a will be in this direction here. So this is our ax. Okay, so in this case, now you're also given this 3 and 4 here, from which you can calculate this angle. You can calculate this angle here, which is obviously equal to theta, and this will become tangent inverse 3 by 4, so which is become 36.87 degrees. So we know the angle here. Okay, now as you're given that the unstretched length of the spring is 1 meter, but obviously the current length of the spring you can calculate from this triangle here. So the current length of the spring, so if you say that the length of the spring will become equal to, in this case, which is 3 square plus 4 square under the root, and this will become 5. The current length of the spring is 5, and the unstretched length of the spring is 1 meter. So this means that if the length is 1 meter, there will be no force in the spring, but the current length is 5 meter. So this means that the stretched in the spring is 5 minus 1, which is 4, and this 4 is responsible for the spring force. So we can say that the x, which is the stretched in the spring, is obviously equal to LSP minus 1. So x in this case will be 5 minus 1, which will be 4 meter. So you cannot just use this 5 in the spring force equation, which is this Fs equal to kx. So you cannot use 5 in this x. This x should be either the stretched or compression in the spring. So you will need to properly calculate this, and which we have done here. And k is given, which is 10. So if you multiply 10 with the stretched in the spring, which is 4 in this case, so this will become 40 Newton. Uh, in the previous years, the students are making these mistakes that they will to calculate the spring force, they will just use this 5 here, which is not correct. 5 is not the stretch in the spring. This is just the length of the spring in the current position. But the you will need to subtract the 1 from here, which is the neutral position or the unstretched length of the spring. So you will have to use this 4 here. So now we know the spring force, and we can now split the spring force into two components in x and y direction. So this will be the spring force. We know that this is Fsx, sorry, y, and Fsx. So this is the x component of the spring force, and this is the y component of the spring force, because this is our coordinate system here. So now if we just use summation of all the forces in x direction equal to max, and again we are taking this is our positive direction. So in this case, we can calculate the now all the forces in x direction. So in this case, we have the spring Fsx in x direction, but it is negative, so this will become Fsx and equal to max. There is no other force in x direction here. There is only one force in x direction. So if you just put the value of this Fsx, which you can calculate from the angle and Fs. So in this case, because this is adjacent to angle theta, so it will be just Fs cos angle. So it will become 40 cos of angle, which is 36.87, equal to the mass is given, which is 10, and ax. So in this equation, the only unknown here is ax. So you can calculate ax, which will become equal to minus 3.2 meter per second square. And the negative here is because we assume that the acceleration is in the positive direction, but it is not in the positive direction, it's in the negative x direction. So this negative is because the acceleration is in negative x direction. So you will always assume that the acceleration is in the positive x direction, but then the calculation will provide you the exact direction of the acceleration.